Okay, so so far we've talked about a couple of different theorems. So we'll continue our discussion of theorems. So next theorem we are going to talk about is called the source transportation. Now, we had the source transformation, and this one is source transportation. So, okay, source transportation. Now, what does source transportation mean? It's actually pretty straightforward, but once you start thinking about it. So let's imagine that you have 3 nodes, 1, 2, and 3. And let's say you have a so there are 2 versions of it, for current source and for a voltage source. So we'll do it with voltage source. So let's say you have a voltage source like that. Let's call this V, right? Now, what are the voltages between these 3 nodes, if you think about it? The voltage between nodes 1 and 2, V1, 2, which is this voltage, 0. What is V, I guess, 1, 3? Is capital V, right? And so is V2, 3. So source transportation says, in the case of voltage sources, this network consisting of this one source and 2 nodes, is exactly equivalent and indistinguishable from this network. So it says, in my head, thinking about these things as topologies, right? I think about this as a tube, like maybe a toothpaste tube. I can squeeze it in and then get it out, and it goes into these 2 branches, right? So I can slide this voltage source in there, and it splits into 2, in 2 opposite directions. Okay? So if you think about that, why is that true? Well, let's see. Let's compare the voltages here. So now, what is the voltage V12 in this new network? 0, right? Because they have 2 voltages in opposite directions and they are of equal value, opposite polarities. How about V13? It's V, capital V. And how about V23? It's capital V again, right? So since all 3 voltages are exactly the same at all times for all values of other currents and everything, so these 2 are equivalent. There's no other alternative. So you can always replace this with that. You can actually squeeze it out, or if you have 2 that are identical, you can actually absorb them into one thing. So that's the one for voltages, but we know that everything has a dual. So what is the dual of that for currents? Well, the dual for currents looks like this. So if you have a current source going between, let's say, node 1 and 2. So this is 1, 2. Again, it's a 3-node combination, and 3. And 3 can be attached to other things, but as far as we are concerned, it's this part that matters. This says it's equivalent to the current source being split into 2 currents, 1, 2, and 3, with the same values, I. Which again, you can see by looking at the total current that's drawn out of each node. So what is the total current that leaves node 1 in this case? Let's call those. So I1 is capital I, right? The total current that leaves node 2 is negative I, negative capital I, right? And the total current that leaves node 3 due to this circuit is 0, right? So how about it here? So the total current that leaves node 1 is capital I. The total current that leaves node 2 is negative capital I, because capital I is injected into node 2. And the total current that leaves node 3 is the algebraic sum of these 2, which is 0. So these 2 are equivalent. You're transporting a source That's what's called source transportation. This is actually useful, for example, in transistor circuits later on when you convert the pi model to T model or the T model to pi model. There are two models of the transistor. And we use this. We take a current source and put it somewhere, and then we take it out of the same place, and we do the same thing. This is also valid for dependent current sources and voltage sources. You can also do it with dependent current, because it's a mathematical relationship, right? So if I have a dependent current source going from this node to that node, I can actually break it into two dependent current sources that depend exactly on the same thing, and they're exactly the same, and use the same theorem. So let me give you an example of how it's applied and how it's used. So, or maybe a couple examples, perhaps. So the first one for this guy would be four ohms, 3 ohms, 6 ohms, 36 volts, and 2 ohms. And the question is, what is this current? And I'm going to just draw both examples here now, one for the current and one for the voltage. I'll come back to it later. This is 4 amps, 2 ohms, 3 ohms, 20 amps, 6 ohms, and 18 amps. Okay. So that's for that. All right, so let's start with this one. So here we have a voltage source here, right? So we can use the source transportation. We can squeeze it out into these two branches. When we do that, this circuit will look like this. So I'm going to just make a modification on this, if it's okay with you, if you have already taken down the original problem. So basically what happens is that I can put these two here, except for the fact that I forgot. What was the value of the voltage source? Okay, so you get a 36 here and a 36 here to ground, right? But when you do that, you notice that, okay, well, if you call this ground, doesn't matter. If you take this, you can actually take these two branches and put them on the outside. I can take this and put it here. And I can take this and put it here. And get rid of these, right? Fair? So now, what do I have? So I have this thing. Now, I can actually even make it simpler by converting this to doing one of the two things. Either looking at this and writing its equivalent, Thevenin equivalent, and showing the Thevenin equivalent of that one. Writing them as Thevenin. Now we can use some of the other things we've developed already. So what is the Thevenin equivalent of this one? What is the voltage you will see across this when it's open circuit, if it's not connected to anything? What is the voltage across here? If this is 36 volts, this is 4 ohms. Right? What is it? 36 volts. Forget about this. Imagine that this is not connected to anything. What is the voltage across here when it's open circuited? It's 4 ohms and 4 ohms and 36 volts. We have a voltage divider, right? So what's the voltage here? 4 ohms, 4 ohms. 18 volts, half of it, right? Right? The open circuit voltage is going to be 18 volts. And what is the equivalent resistance? What do I see across here when the independent source is nulled? When this guy is 0, which is shorted. So what do I see? I see 4 ohms in parallel with 4 ohms, right? Which is 2 ohms. So that's the equivalent of this guy, this box. right? You need to get comfortable with these. How about this side? What is the voltage I will see across here? This time I'm going to ask someone who's next in that line, in the back, second row.
Voltage divider.
Uh-huh.
3 and 6.
Right.
So
The divider ratio is this resistor divided by the sum of the two. So it's 6 divided by 9. 2/3 of 36, which is 24, right? And then what is the resistance you see when you null it? When you short circuit this, what is the resistance you see across here? Imagine that this is not going to. 3 parallel 6, right? Which is? No. 2 ohms, yeah. It's 18 divided by 9. It's the product divided by the sum. Right? So it's 2 ohms. Okay, so that's what this is. So now I put that resistor in the middle, 2 ohms, and I want to find this current. Now this is a lot easier, right? So what is this current? So it's 24 minus 18, which is 6, divided by 6 ohms. But which way would it go? So it's 6 volts divided by 6 ohms. But which way would that current flow? From right to left, right? So then it would be negative 1 amp because of the direction. So 1 amp is incorrect. We say 1. Okay, so that's for that. How about this one? Let's see if we can apply source transportation. So this one. Maybe the next person in line. How would you apply it? Which source would you apply it to? It's you. White shirt. Yeah. Yes. Which one of these sources would you apply it to? If you want to make things simpler, less coupled. The top one, right? Because it's the one connecting left and right to each other. So you can actually separate the left and right. So you apply it. How do I apply it? I have this 20 amp thing going up. That would go down into this node and come back into this node. So when it goes down into the node, it would be an 18 amps in parallel with this guy, in parallel with the 3 ohms. Then I have the 6 ohms that's still there. And then I have to take this 18 amps back up. So I go, the 2 ohms is there. And then I would end up with the 18 amps going up to compensate that 18 amp that went down in parallel with the 4 amps. So what is this? This is equivalent to a single current source of what value? 6, yeah. In which direction? Up? 6? No, sorry, not 6. This is 20 and 18. What is it? It's 20 amps up, 18 amps down. What is the current? This is 20, this is 18. 2, exactly, yeah. Sorry, if the font is too small. No. Okay, and how about this side? What do you see? 18 up, 4 down. 18 up, 4 down. 14. Yeah. Okay, 14 amps up. So you could actually solve this, but you can even make your life easier by writing the. Now you can actually apply the source transformation. So you can take this 2 amps and 3 ohms and convert it to a Thevenin, which would be what? So what would be the Thevenin of a 2 amps and 3 ohms? So what would be the voltage? You can write it like this, doesn't matter. So if I have a 2 amp in parallel with 3 ohms, 6 volts and 3 ohms, right? And then that one in the middle is still 6 ohms. Now the same deal here, 14 and 2, what do I get? 28. All right. Okay, so what's the current in this thing? So this is what we are trying to find, right? This current, I. So which is this current, I equals question mark. So it's 28 on this side, 6 volts on this side is 22 volts across what? 11 ohms. So it's 2 amps in this direction, so this is going to be negative 2 amps. Yes?
Can you explain how you determine the directions for the 18 amps when you split it? So the second picture.
Here?
To the right.
Oh, to the right.
So there's two 18 amp sources, right?
No. Oh, you mean these two 18 amps?
Right, yeah.
It's the same direction as those two, right? I did that transformation from that. So this current source is that current source. This node is the third node. I took it down here and brought it back up here. So this is what I did. I said, forget about this guy, replace it with this plus that. 18 amps, 18 amps. That's what I did. Okay? Any other questions? No? Yes?
Could you do it the other way, or would that be wrong? Or
Could I do it the other way? You mean?
yeah, like that way or that way?
You mean this going up?
Yeah.
And okay, well think about it. Let's go back to the original representation. Do you agree that I could discuss it in this presentation too? So if I do this, so what you're suggesting, if I understood correctly, and correct me if I'm wrong, you're suggesting that is this also equivalent to going this way and that way, right? No, it isn't, right? Because one takes the current I out of the node, one injects that current into the node. So these are not equivalent. This is equivalent of this guy. Those two oranges are equivalent, and those two blacks are equivalent, right? It seems to have a Halloween theme. Okay. Any other questions? Yes?
I'm a little confused at the top where you give me voltage divided. Sorry, it's to the left. Why did you find the voltage across the 6 ohm resistor in the other diagram?
Here?
Yeah, at the top, like on top. Yeah.
Why did I find what? How or why?
No, why?
Okay, I'm trying to find what the Thevenin equivalent of this circuit is. This is my black box. The whole thing that has a circle around it. How do we determine the Thevenin equivalent? We look at the open circuit voltage, VOC, right? VOC across here, what is it? If this is 36 volts, it's a voltage divider between the 6 ohm and the 3 ohm, which would be 6 ohm divided by 6 ohm plus 3 ohms, which would be 2/3 of 36, which gives me 24. And then I said, okay, to determine the equivalent resistance, I have to null all the independent sources. Nulling 36 volts, whatever it is, it's basically a short circuit. It's a voltage source. So I'm looking at the parallel combination of 6 ohm and 3 ohms, which is 6 times 3 divided by 6 plus 3, which is 18 divided by 9, which is 2 ohms. So this is the Thevenin, this part. Let me just use color codes. This is that. This is that. They're equivalent to each other. Yes. Any other questions? No? Yes?
Sorry, I don't quite understand where you got the 6 volts at 20 amps.
This 6 volts?
Yeah.
Okay. So I skipped a step, really. So do you agree that this parallel combination of 20 amps and 18 amps is 2 amps, right? So do you agree that what I have a circle around can be represented by this? Now, if I extend my circle a little bit bigger and make it into that, this is some Norton equivalent, right? So I do that source transformation. I converted it to a Thevenin like the other one. So when I did that, what's the voltage? The voltage is a product of these two. There's another way to think about it. Think about if you wanted to do a Thevenin equivalent of this circuit, what did you need to find out? Right? VOC. What is the VOC? The voltage across here. 6 volts. What is the resistance? Null the sources. This becomes open, you get 3 ohms. All right? Any other questions? Feel free to ask questions. I have no problem with you guys asking questions, as many as you need. Okay? Yes?
So, as a problem-solving thing, is this just as powerful as nodal analysis, or is there some things that this cannot do?
It's as just solving a problem?
Yeah, just solve.
In certain cases, it's more convenient, but in general, absolutely not. Nothing is as powerful as nodal analysis.
Okay.
Use my H-bomb analogy. But there are lots of problems we can't solve with H-bombs. Almost there's no problem you can solve with H-bomb, essentially practically. You could argue that there's nothing you can solve with H-bomb. Right? Right. But, so this is basically, nothing is as powerful as nodal analysis. Nothing is nearly as powerful as an analysis tool by itself, pure analysis. But these are useful. These are important. Actually, I would argue that these are even more important than nodal analysis. Unless you're developing, let's say, circuit simulators 10 years from now, you will probably not remember nodal analysis exact details of it. You remember, okay, what you may remember, you may say, okay, there was a way of converting this problem to a mathematical linear algebra problem. I think there was a formal way of writing it. And that's fine. But what these things tell you, particularly some of these other ones like superposition and all those things, are basic principles of equivalency or reduction of a bigger problem to a smaller one. Or thinking, it gives you ways to break it into smaller units. You know, eventually, you want to be able to, again, this is a very rough analogy. For design, you want to be able to understand, create your own Lego blocks and understand them well enough so you can attach them to each other to do things that you want. Now, understanding these units is a lot easier when you simplify them to things that our brains can handle. When you create more abstractions, say, okay, so that's a Thevenin equivalent, that's a Norton equivalent of that. Okay, so I don't need to worry about that. So if I want to make this current 0, then I have to make this such and such to make that 0. And again, it's an example of an engineering principle. You may apply it in a completely different, you may apply it in a mechanical system, you may apply it in a financial system, but it's that kind of principle. So this is a platform for you to think about these things. Yes?
By the way, why do you, for that one, why do you get -1 amp again?
Because this side is 24 volts, this side is 18, right? So which way would the current flow? From left to right or right to left? From right to left, right? But the direction I've defined for this is from left to right, which is fine, therefore it becomes negative. If I had defined this, if I had drawn this, I could have basically, when I asked for the question, I could have drawn this arrow this way, and then it would have become 1 amp. But when that arrow is defined that way, that's the direction that's defined, and then it's an algebraic value of that. It can be positive or negative. And if you mess this up, it will mess everything up. If you're kind of inconsistent with your polarities, if you don't stick to your gun with the polarities and orientations of things, almost certainly things will break down. Any other questions? All right. If not, let's continue. So there's another theorem that I think actually is quite important. So let's move to the middle board. Let's start erasing stuff. Okay, so the next theorem, I guess, would be number 6, right? Yeah. This is called the substitution theorem. This is actually very important in my mind. Not necessarily for this class. I mean, we use it in a couple of examples in this class, but in things that come later, particularly in electronics. And I'll tell you why it is, and you probably will forget it by the time you get there. So I don't know. I'll tell you now. Maybe you remember. One or two of you may remember by the time you get there. So the substitution theorem says the following. Says that if you have somewhere in a large network, so let's say this is a large network, and somewhere you have an element E that's attached between two nodes. Nodes M and N, I don't know. Doesn't matter. It says that you can actually, if this element has when it's in that network, within that network, it has a voltage V and a current I flowing through it. So this is that you can think about it as a resistor somewhere in a big network. one of the resistors or one element. It doesn't even have to be a resistor. It can be inductor or it can be anything. If you have a branch which experiences a voltage V and a current I, this is equivalent to, you can actually take out this element and replace it with a voltage source. Excuse me. Of value V, or you could take it and replace it with a current source, ideal voltage source or ideal current source of value I. Oh, lowercase I, sorry. This is actually interesting, isn't it? So if you have a resistor in a network, in a big circuit, and you see, like, you look at it and say, its voltage is 2 volts. I can take it out, replace it with a voltage source of 2 volts, and nothing else in that network will change.
What about its impedance?
What about it? What about it? Just, the question is, what about its impedance?
Well, like,
And I'm saying, what about it?
you put in like an ideal voltage source. Wouldn't it change like the impedance?
Sure, it changes the impedance, that's seen, but it doesn't change anything else in the network. It says that nobody else will notice the change. This may sound a little bit counterintuitive in the beginning, but just like, this is important and very valuable. It says, you know what? As far as everyone else is concerned, this is imitating that behavior. It's creating that voltage. And when you do that, by the way, the current is going to be I. And when you do this, the voltage is going to be V. And nobody else will notice anything. Okay? So, how do you prove it? Well, the proof is actually pretty kind of straightforward when you think about it. So the proof is like this. So let's say when I have this branch, I take a voltage source of value V and put it here, of the same value V. And this end is open. Does this affect anything? No, right? I mean, when I say it's open, what do I mean? I mean it has an infinite resistance, really, right? So let's say this is an R that goes to infinity. So it means like an open. This is not going to draw any current, right? At this point. But when I have something like this, what is the voltage difference between this node and that node? What is the voltage across here? What is this voltage, Vx? Is it V? These are at the same voltage, right? So both of them go up V. So this voltage is 0, right? So as I start reducing R from infinity to a lower value, would there be any current flowing through this guy? No. So for any value of R, there's no current flowing, including R equals 0. So when I make R equals 0, what I have is really essentially this thing. So I have an ideal voltage source in parallel with an element. What is that? An ideal voltage source in parallel with an element that's not an ideal voltage source? It's the ideal voltage source, right? We talked about this when we were talking about ideal. And the same thing is true about the ideal current source in series with an element that's not an ideal current source. It's the current source. So for all intents and purposes, I can get rid of it because this would be the same, so that would prove that part, the first part. If I want to prove the second part, can I erase this? Okay. To prove the second part, I'll do this. Say, hey, you know, there's current I flowing through here, right? This is sure. Say, well, you know what? I put a current source in parallel here with this short of the value I. Said, okay. Would this mess anything? No. This current is going to be I. This is going to be I. And what is this current going to be? This I is 0. So I have an element, the current across which is identically 0. Can I replace it with an open circuit? Would it make any difference? An element whose current is always 0 is what? An open circuit, right? So I can replace this with an open circuit. So now I am in that situation that I have a current source in series with an element. That's not an ideal current source. which becomes equivalent to just the ideal current source. You don't need to worry about this. So now, the way it's going to be used, and just listen to it in case you will remember it by then, is that when you have multi-stage amplifiers in electronics, you will see electronics, first you go through like single-stage amplifiers, then you see cascade of amplifiers. So the first amplifier takes the output of the first amplifier, second amplifier takes the output of the first amplifier as its input, and then its output is amplifying it further, right? So that's one, each one of them has a gain of 10, you have 3 in a chain, so you get a gain of 1,000. 10 times 10 times 10, right? Each one of them amplifies by a factor of 10. That's fine. When you analyze those at a transistor level, what you do is that you calculate the gain of the first stage independently with the input resistance of the second one. So you take the input resistance or the input impedance of the second stage. So let's say you have amplifiers, 3 stages of amplification, right? And each one of them has an input resistance. Let's say, so let's call this A1, A2, A3, and each one of them, so this has an R in, let's call it R1, R2, and R3. So inside these things, there are a lot of transistors, resistors, other things, right? So when you're analyzing, you say, well, instead of analyzing all of them as a whole, I analyze this plus a load of R2, because that's what it sees, right? So this is A1 and R2. And I calculate a volt. So this is V in. This becomes some voltage, some V1, in terms of V in. So this would have some proportion. It becomes A1, V1, V in, right? That's the voltage that this network will have at this point. When you want to stage the second, when you want to analyze a second amplifier, you don't need to worry about what's inside this thing anymore. All you say is that I substitute all of this with a voltage source of V1 now. So I substitute this because I know what this voltage is, it's V1, and I assume that it's driven by an ideal voltage source at that node. And I repeat the same thing up to here. I analyze this with R3 as the load, and then I put this here, and then whatever our load is here. And I go through that process. I calculate, I reduce it to 3 independent calculations, which makes my life a lot easier. That's how substitution theorem is actually used. One practical example of that. Hopefully you will remember it by then. They say if you want to remember something, at least you need to say it to yourself 3 times at least. For some of you, it may be once, depending on your age. You know, as your age increases, that number increases. But so that's good. For, anyway, so let's do a simple example just to see it in action, and we'll take it from there. So this example is pretty simple. So let's say, this is 20 volts, 4 ohms, 4 ohms, 6 ohms, 3 ohms, and let's call this Vs. And then this is 2 ohms. So the question is, if this is the current, I want to choose Vs in such a way that this I becomes 0. So I want this I to be 0. What is Vs? So what do I do? How do I use substitution theorem? Or you could make it 1 or whatever, some other number. This is the simpler example. So substitution theorem says that I can replace this branch with a current source of value 0, which means that it's going to be an open circuit. So I can open circuit this, and all I need to do is just to make sure that these 2 voltages are the same. So now I can calculate this very simply because I know what this voltage is. What is this voltage? 10, right? It's 20 equally divided, so it's 10 volts. So I want to make this voltage 10 volts. So this voltage is the voltage divider ratio of this. So it's 6 divided by 9 times Vs is 10 volts. Right? So it's 2/3, it's 30 over 2, 15 volts. Make sense? Okay. Okay, so that's for that. All right, moving on. So the next theorem we are going to talk about is the maximum power transfer. Maximum power transfer. And this probably you have seen somewhere. But so I'm going to go over it pretty quickly. So let's say you have a voltage source, Vs, that has a resistance Rs. The question is, so let's say you want to get most power delivered into this resistor RL. How would you do that? How do you choose RL to get the most power transferred? And this is called matching. And there's a more general form of this, which you particularly use in the power systems and RF system, radio frequency system, or high frequency systems, which basically calls conjugate matching, when you look at this as an impedance as opposed to a resistor. So, but let's do it for the resistor first. So, what is the power delivered to RL? Well, you have to look at its current and voltages, right? So, what is the power in RL in terms of the current, or let's say in terms of its voltage? So, let's say this is V here. What is the power delivered to the resistor RL when you know its voltage? V squared over R, right? So P delivered, PL, is V squared over RL. Now what is V in terms of Vs? Exactly. V is RL over RL plus RS times Vs. So I plug that in, I get RL squared divided by RL plus RS squared times 1 over RL times Vs. Right? Vs squared. Right? So one of these cancels that. One of the RLs cancels the other RL. So this is what I'm left with. So if Vs is constant, I'm looking at RL over RL plus RS, and I'm trying to maximize this quantity. So I'm trying to maximize this quantity. How do you maximize a quantity? You differentiate with respect to it and set that that derivative to 0. Well, that optimizes it. It may minimize it. So you can actually plot this, and what you see when you plot this versus RL, P versus RL, you'll see that it looks like that. So you're trying to find where that point is. So how do you do that? Differentiate with respect to RL. So dPL divided with dRL. So the derivative of this thing is the derivative of the numerator times the denominator, which is basically RL plus RS squared, minus the derivative of the denominator times the numerator, which gives me 2 RL plus RS times RL, divided by the denominator squared, sorry. Times Vs, which doesn't matter. So I'm setting this to 0. That means that the numerator has to be 0. One of the RL plus RS's cancel each other. So I'm left with RL plus RS equals 2 RL. One of these RLs cancels the other one. Therefore, RL must be equal to RS. So you get the maximum power transferred when this resistor and that resistor are equal. You can do it numerically. You just pick 1 kilo ohm and 1 kilo ohm, and then pick 1 kilo ohm and 1 ohm and 1 kilo ohm and 1 mega ohm. You may say, sometimes people say, wait a second, but the larger I make RL, the larger that voltage is. So I should be able to make more power delivered. No, why not? Because the larger you make this, the smaller your current becomes. So at some point it becomes diminishing and negative returns. When you do that, what happens is that your current becomes so small that the voltage drops totally. You get all of the voltage across here, but when you divide it by RL, it goes down. And the same thing is true if you make it very small. If you make it very small, yes, the current is going to be larger, but the voltage is going to be small. So it's a product of two quantities you're trying to maximize, right? This is really V times I. You remember power was V times I. So we just wrote it that way using Ohm's law. OK, any questions on that? No? All right. So the last one we're going to do today. Again, this is not a fundamental theorem in the same, it's less fundamental but more useful. It's something useful to know. It's good for solving problems. And it's relevant to certain things. So it's good to know about this. It's called the Y-delta conversion, or delta Y conversion. I can put a number in front of it anyway, it doesn't matter. Which is a special case of mesh star transformations. So this is something that you'll see and gives people in the beginning when they're doing circuit analysis sometimes trouble. If you see a triangle of resistors, let's say, just keep it consistent with my convention. Okay. A, B, C, 1, 2, 3. So you have a 3-node system consisting of 3 resistors forming a triangle, or delta. If you look at it upside down, it looks like a capital Greek delta. Excuse me. So it says it's equivalent to a star or a Y connected between these 3 nodes, 1, 2, 3. You can call this R3, R2, and R1. And R1 is going to be RB, RC divided by RA plus RB plus RC. And you can see it's symmetrical, right? Because this resistor is determined by these product of these two over the sum of all 3. So by that argument, then you can tell me what the other 2 are going to be, right? If I ask you what's R2 connected to this node, it's going to be product of what? The 2 that are connected to that node, A and C, RA, RC, divided by the same sum, RA, RB plus RB plus RC. And similarly, R3 is going to be AB, RA, RB, divided by RA plus RB plus RC. So it allows you to go from this to that. Or likewise, if you want to go backwards, it actually turns out that RA, that expression is a little bit longer. It's R1, R2 plus R1, R3 plus R2, R3 divided by, what do you think it's going to be divided by? It's divided by one of those 3 resistors. Which one is it going to be for RA? Which one has it? It has to be by symmetry. R1, exactly, right? Because if it were R2, then why not R3? You look at it in the mirror, right? So, and similarly, you can do it for the other ones. It's the same sum. So that's called a, because this looks like a Y, and if this is upside down, it's a delta. And generally, there are these transformations that are called mesh star or star mesh. So star would look like this. And a mesh is a connection of all possible resistors that can be connected among these nodes. In this case, it's a 5-way. So it's like that, it's like that, it's like that, that, and that, and that. So all of them are connected to each other. So these are mesh and star conversions. This is useful for a lot of, actually several different things, particularly 3-phase systems. Now, you may or may not deal with 3-phase systems. If you're dealing with power systems or power conversion, you will deal with 3-phase systems. The idea here is that you have 3 different sinusoids with 3 different phases. One is 0, one is 120, one is 240 degrees. So there are three vectors that are 120 degrees apart, and they're rotating, and then this will allow you to solve problems. Also, this is useful, for example, when you're trying to be annoying, give you those bridges with the resistors in the middle and all those things. You can convert it to something that's not a bridge, and then deal with that if you have to. Again, it's not a very fundamental theorem. It's a useful thing. Any questions? If not, okay, I'll see you next time.